What problem does the proposed method aim to solve in the context of logical reasoning tasks?
The proposed method aims to solve the problem of the reversal curse in the context of logical reasoning tasks. The reversal curse refers to the phenomenon where an auto-regressive large language model, LLM, struggles to generalize from learning a relationship in one direction to predicting the reverse relationship. This issue hinders the model's ability to deduce indirect conclusions or manipulate learned knowledge effectively. The method theoretically analyzes the dynamics of training in auto-regressive models, such as bilinear models and one-layer transformers, to understand why the reversal curse occurs. The analysis reveals that the asymmetry of model weights, specifically the logits from one token to another, is a core reason for the failure of LLMs in certain types of logical reasoning tasks. By studying the training dynamics and properties of model weights, the proposed method sheds light on the challenges faced by LLMs in reasoning tasks that require multiple steps of inference or manipulation of learned knowledge.
How does the proposed method work to address the reversal curse in auto-regressive LLMs? Please illustrate step by step.
The proposed method addresses the reversal curse in auto-regressive LLMs through theoretical analysis and empirical validation. 1. Theoretical analysis. The method starts by studying the training dynamics of auto-regressive models, specifically bilinear models and one-layer transformers. It analyzes the asymmetry of model weights, where the weights from one token to another are not necessarily symmetric. This asymmetry leads to the reversal curse, where the model struggles to generalize to the reverse direction. The analysis reveals that the weights associated with the reverse direction do not get trained effectively during training, leading to the reversal curse. 2. Empirical validation. The method conducts experiments using multi-layer transformers based on the GPT-2 architecture to validate the theoretical results. It constructs synthetic datasets where entities and relationships are randomly assigned, and the model learns both direct and reverse relationships. The experiments show that during training, the model's next token probability for training data increases significantly, while for validation data, it remains unchanged or even decreases. This empirical validation confirms the theoretical findings of the asymmetry of model weights, causing the reversal curse. 3. Key findings. The method demonstrates that the asymmetry of model weights, particularly the logits of a token given another token as input, is a core reason for the reversal curse. The model's inability to effectively learn the reverse direction during training leads to the failure in generalizing to the reverse relationships. The empirical results align with the theoretical analysis, showcasing the practical implications of the proposed method in addressing the reversal curse in auto-regressive LLMs. In summary, the proposed method works by identifying and analyzing the asymmetry of model weights, which hinders the model's ability to generalize to reverse relationships. Through theoretical insights and empirical validation, the method sheds light on the mechanisms behind the reversal curse in auto-regressive LLMs and provides a comprehensive understanding of how to mitigate this challenge.
What are the theoretical benefits of using the proposed method compared to existing alternatives in addressing the reversal curse phenomenon?
The theoretical benefits of using the proposed method in addressing the reversal curse phenomenon lie in the detailed analysis of the training dynamics of auto-regressive models, specifically bilinear models and one-layer transformers. The paper provides a deep understanding of why the reversal curse occurs by studying the asymmetry of model weights, which is a core reason for the failure of LLMs in certain types of logical reasoning tasks. The analysis reveals that the weights from one token to another are asymmetric, leading to the model struggling to generalize to the reverse direction. Additionally, the paper empirically validates the theoretical results on multi-layer transformers, confirming the asymmetry of model weights and the difficulty in deducing indirect conclusions without proper training steps like chain of thought. This method offers a unique perspective on the reversal curse phenomenon, focusing on the training dynamics rather than expressivity, which is a common approach in existing works. The detailed theoretical analysis and empirical validation provide a solid foundation for understanding and potentially mitigating the reversal curse in autoregressive LLMs, highlighting the importance of considering training dynamics and model asymmetry in logical reasoning tasks.
How is the asymmetry and intransitivity of model weights explained in the paper, and how does it contribute to the failure of logical reasoning tasks in autoregressive LLMs?
The paper explains that the asymmetry and intransitivity of model weights in autoregressive large language models, LLMs, contribute to the failure of logical reasoning tasks. The asymmetry is demonstrated by the fact that the weights from one token to another are not equal in both directions. For example, in a bilinear model or a one-layer transformer, the weights from token A to token B may increase during training, but the weights from token B to token A may not increase proportionally. This asymmetry leads to the model struggling to generalize to the reverse direction of learned relationships, such as from A is B to B is A. On the other hand, intransitivity refers to the phenomenon where increasing the weights from token A to token B and from token B to token C does not necessarily increase the weights from token A to token C. This lack of transitivity hinders the model's ability to deduce indirect conclusions using separate knowledge learned during training. The paper empirically validates these properties in multilayer transformers, showing that the model weights associated with certain logical relationships are not effectively trained, leading to the model's inability to perform logical reasoning tasks accurately. Therefore, the asymmetry and intransitivity of model weights limit the model's capacity to deduce indirect conclusions and contribute to its failure in logical reasoning tasks.
What experimental validation was conducted to support the theoretical results on the reversal curse and chain of thought using multi-layer transformers?
The experimental validation conducted to support the theoretical results on the reversal curse and chain of thought using multi-layer transformers involved training multi-layer transformers based on the GPT-2 architecture. The experiments focused on synthetic datasets constructed to test the reversal curse and chain of thought phenomena. For the reversal curse, the model was trained on pairs of sequences representing relationships in both directions and then tested on unseen directions. The results showed that during training, the next token probability for training data increased significantly, while for validation data, the next token probability remained unchanged or even decreased, confirming the theoretical predictions. Additionally, the asymmetry of model weights was empirically validated for multi-layer transformers, showing that the model weights associated with the unseen direction were hardly trained. For chain of thought, similar experiments were conducted where the model was trained on triples of sequences representing direct and indirect implications, and then tested on indirect implications. The results demonstrated that the model could learn direct implications well, but struggled to deduce indirect implications directly, aligning with the theoretical findings. Furthermore, the intransitivity of model weights was empirically validated for multi-layer transformers, indicating that training the weights associated with two intermediate steps did not necessarily lead to an increase in the weights associated with the final implication. These experimental results provided empirical support for the theoretical analyses of the reversal curse and chain of thought using multi-layer transformers.
Based on the results presented in the paper, what are the implications for the development of future language models in terms of addressing logical reasoning challenges?
Based on the results presented in the paper, the implications for the development of future language models in terms of addressing logical reasoning challenges are significant. The paper highlights the challenges faced by autoregressive large language models, LLMs, in tasks requiring logical reasoning, such as the reversal curse and the necessity of chain of thought, COT. The theoretical analysis and empirical validation on multilayer transformers demonstrate the asymmetry and intransitivity of model weights, which hinder the model's ability to deduce indirect conclusions and complex reasoning tasks. This suggests that future language models need to address these issues to improve their performance in logical reasoning tasks. Specifically, future language models should focus on addressing the asymmetry and intransitivity of model weights to enhance their ability to deduce indirect conclusions and complex reasoning steps. By understanding and mitigating the reversal curse and the limitations of direct reasoning, language models can be better equipped to handle tasks that require multiple reasoning steps and indirect implications. Additionally, incorporating techniques like chain of thought (COT) can help models in generating intermediate reasoning steps, leading to improved performance in complex logical reasoning tasks. In conclusion, future language models should prioritize addressing the asymmetry and intransitivity of model weights, as well as incorporating methods like COT to enhance their logical reasoning capabilities. By overcoming these challenges, language models can improve their performance in tasks that require complex reasoning and multiple logical steps, ultimately advancing the field of natural language processing and artificial intelligence.